Welcome to the 8th lecture of Solar Electric Energy Systems. Today we will talk about simulations of irradiance, of PV systems and of microgrids. Let's first talk about microgrids. What is relevant there? First, obtaining the data. So we discuss the different tools for simulation and design. We make a short introduction of the Homer Pro software. Also the exercise will be about it, presented by Mr. Khatibi. Then we have some definitions. We will simulate exercise number 6, the PV system in Rio de Janeiro, which we already solved manual, but this time with Homer, more sophisticated. Let's take a look in a general overview of our microgrid system. So you have the solar photovoltaic systems, where we discussed a lot already about it, but in some places wind turbines are the preferred or an additional option. Sometimes you need a backup generator. Also, energy storage plays a major role. Some locations are interconnected to the utility, so you either do grid feeding or take some electricity from the utility. Sometimes they are quite unreliable or only can provide a certain amount of power. Also, we have discussed about the load. It's usually the first thing we do, just obtaining the load data, not only the accumulated energy, but also the energy needed during a day, the so-called load profile, and during the year. So in order to design it properly, we have to check the user needs. So the questions to be answered: which kind of renewables sources should I choose? This depends on the location, but also on the preference of the customers. Do I need a storage system? Sometimes it's sufficient to power directly from renewables, for example, pumping systems powered by a PV panel, and the actual storage will be the tank with the pumped water. How big should my battery systems be? So basically it's also the question, how reliable should the system be? Do I need a backup generator? How will my system grow with growing demand? What if the fuel price changes? Such a system lives for 25, 30 years, and during that time a lot may happen. Also, for example, increasing fuel price, and this changes the whole economic. So the consideration in system sizing is the correct calculation and estimation. So we have to have precise data such as local solar and wind energy potential, because if you make a mistake there, the whole system design fails. We have to have precise data about the electrical load and the users, the importance of components such PV panels, wind turbines, capacity and sizes. Usually in the simulation package you find a big catalog of famous brands of manufacture of those components, for example PV panels or wind turbines, but also of batteries. The importance of backup systems, so battery storage or a hydrogen tank, if you prefer a seasonal storage, or if you have to have a seasonal storage, or the generator. It's also relevant how fast they can act. There's no problem at a battery storage, it acts basically immediately. But if you have a diesel generator, it takes for some minutes to start up when it's cold. And this you have to consider. You have to have bridge power, maybe also an additional battery, to feed the rest of your systems during this 1 to 8 minutes, which it takes to ramp up the backup generator. Other components, it's also inverters. You see that you saw already that the efficiency is changing at different load conditions, but also same applies for charge controllers and the maximum power point trackers. Also, the systems costs and the energy unit costs are relevant, because of faulty designed systems leads to instability, power outage, finally to higher costs and losses. Not only from the system side, but also from the customer side. If you, for example, connect a hospital or refrigerating units there, you will have additional damage. Obtaining the required data. We discussed in the second lecture already about it. When we talked about the irradiance measurements, we do this usually via so-called pyranometers, which you see above in the image. Usually meteorological measurements are carried out in a horizontal way. So you have meteorological stations which measure for many years. As we see later, most of the data available is since the 80s. The wind power, which is below there. The problem is it's not perfectly suitable for the designing of photovoltaic systems, because usually we apply the photovoltaic system in an inclined surface of 30 degrees in Europe, or if you go further north, even steeper. Only if you are close to the equator, horizontal mounting is a preferred option. Same applies for wind. Usually the meteorological stations are mounted in a height of 5 or 10 meters, while wind power systems nowadays, or large-scale systems, are 100 meters above the ground and more, and the wind condition may change there. You can interpolate this, but is also subject to some errors because the roughness of the terrain is not correctly estimated, and also the number of full load hours is changing. Usually the wind is more constant the higher you go, and this also changes the whole economics of your system. So energy potential and meteorological data collection. So you have best would be if you measure it locally with devices as local pyranometers or local anemometers in the exact application. So means inclined surfaces for the case of photovoltaics, and in the height of the future wind turbines for wind power. It is related to some costs, but if you compare it to the costs of falsely designed system, this is relative. Also, temperature plays a role because, as you know, the photovoltaic generator produce less power when the temperature is higher. Also, for the wind, if you have higher temperature, the air density changes, and therefore the power output may differ. The same applies for pressure meters. So if the pressure is higher, then the density is higher, then the power output of a wind power system is increasing. Wind direction sensor in general are time-consuming process. Minimum is at least 1 year to carry out the measurements to take account the seasonal effects. Best would be a whole decade of measurements, or at least 5 years. Organizations which do that, the German Weather Service, but also many international weather services, or you would use satellite data or data from airports, which are quite limited and not available everywhere. As I mentioned, just the use of satellite data, for example, MERA, or data from NASA is a preferable option. I did this quite a long time ago and compared it in Berlin at my time. During that time, the differences between satellite data and local mesh data have been quite severe. Nowadays, this is improved. Also, you can use data collection of ground-based measurements, which also have an interpolation option, such as Meteonorm or PVGIS. Meteonorm has implemented 8,000 stations around the world. PVGIS is for free, but it only contains data from Europe, from Africa, and some part of Asia, basically the Middle East. This is the MERA data. So you have here the resolution of the MERA. You can even distinguish between different wavelengths. Also albedo, always quite relevant for satellite data, because sometimes the satellite doesn't see ground reflection. It may see reflection from cloud layers. The temperature may differ at different heights. Air pressure plays a role. Wind speed can measure also via a satellite, but is basically by cloud movements. But basically, as I mentioned, there are different layers of clouds, and you don't know which is the relevant cloud layer or which is relevant for the ground. This is just to mention the data collected from meteorological satellites. It's available for the whole world, and you have different accuracies. So as I mentioned, MERA, which is supplied by NASA data. There is ERA5, which is data from the European Union. Same applies for PVGIS. So MERA 2 offers a resolution of 50 kilometers. So this is 0.5 degrees in latitude, 0.625 degrees in longitude. You have data there since 1980. The resolution here around Paderborn, here you see Paderborn here, and this is the resolution of 50 kilometers or 0.5 degrees in latitude. Era 5, so this is made by the European Centers of Medium Range Weather Forecasts. You have a better resolution of 30 by 30 kilometers, but data only available since 2010. And basically both serve for estimating the local energy potential. Here we see a short movie about the estimation of solar irradiance using the Meteonorm database.
In this video I will show you how to estimate solar irradiation using Meteonorm software. First, go to Meteonorm website. Click on Download button and install the software. Open the software after installation. If you don't have a license, continue in demo mode. First step is to select a particular location. You can either search for the location, or use the map tool to find it. We will use the map and key in latitude of 15 degrees and longitude of 45 degrees. Then click on Create New Location button. Give a name to the new location. We will name it Location 1. Then click Save button. Close the Map tool window. You can find the location in User Defined tab. Click on Select Location for calculation. Then click Next button. In this section you can specify the orientation and tilt angle you require. We will change tilt angle to 15 degrees, then click Next. Here, you can modify some data settings. We will keep the default settings and proceed to next section. In this section, you can specify output format. Let's keep standard format. Final section shows the results of calculations. There are several tabs you can explore. Monthly diffuse and global irradiation on horizontal surface in kilowatt-hours per meter square per month. A trend of daily irradiation throughout the whole year. Temperature profile of the location. Precipitation. And sunshine duration in hours for each month. And most importantly, a table of monthly and annual values for several parameters including global horizontal irradiation, and global tilted irradiation at the specified tilt angle, in this case 15 degrees. You can copy the table, then paste it in Excel spreadsheet. Then you can convert the monthly irradiation on inclined surface into average daily irradiation by dividing by number of days in each month. You can also find daily irradiation averaged throughout the year. You can save all the results to a text file by clicking on Save All Results to Disk, then choosing the output format. However, in demo mode this function is not available. In this video I will show you how to estimate solar irradiation using PVGIS database. First, go to PVGIS website and click either Europe, or Africa for Africa and Asia. We will choose Africa and Asia. You can either search for a location or key in latitude and longitude. We will key in a location in Middle East with 15-degree latitude and 45 longitude. In PV Estimation tab, you can assess the performance of grid-connected system. You can specify system losses, tilt angle, orientation, and choose tracking options. In Monthly Radiation tab, you can get estimated monthly solar irradiation. Similarly, you can get daily irradiation from Daily Radiation tab. In Standalone PV tab, you can design a standalone PV system. Let's estimate monthly average irradiation for our location. We will estimate horizontal irradiation and irradiation at optimal angle. You can also estimate irradiation at any specific tilt angle if you want. This window shows us the results. We can see optimal tilt angle for this location, which is 17 degrees from horizontal. We can see average horizontal irradiation per day for each month, and irradiation at optimal tilt angle, as well as the respective monthly optimal tilt angle. There is also annually average daily irradiance estimates at horizontal and at optimal tilt angle. Here is also a graph to visualize horizontal irradiation, and irradiation at optimal tilt angle of 17 degrees. Another graph shows how optimal tilt angle changes throughout the year. You can also save the results into a test file or PDF.
This was the example using a PVGIS for the irradiance potential. So there's different software available for system sizing. We will just discuss the main out of them. You have typical input requirements as loads to be supplied. They are rather important. The consumption plan, so you have the load profiles, the daily, weekly, could also some differences between working days and weekends, or monthly, depending, for example, on agriculture, whether more or less energy is needed. This is the same applies for seasonal. Also, the years may change in the load profiles. You have the geographical location of installation, the latitude and longitude, which you have to give as an input. The desired types of power sources, so a solar, wind generator, a grid, and so on. The desired types of storage, so either battery storage is the most easiest one, but it's very hard to apply it for seasonal storage because the required capacities are rather large and the number of cycles are rather low. So you would have one cycle every year only. And so, for example, for Germany, hydrogen is a preferred option. So you have other necessary or desired components, for example, inverters, converters, and controllers. Also to consider the financial side conditions, the currency, the inflation rate, the interest rate. It doesn't play a role at the moment in Central Europe, but in many countries you have quite inflated interest rates, which make it rather difficult to calculate a renewable energy system, which rather work for a long time, and the interest rates has quite a big impact on them. Subsidies. Due to the last decrease of photovoltaic and wind power during the last years, mostly subsidies are not anymore required. Remember the last lecture on the market. Remember this map where I showed you all the countries where photovoltaic is cheaper than diesel generation. So you don't depend anymore on subsidies. The other way around could be difficult if conventional energy sources are subsidized, for example, diesel generation. I experienced that in Brazil. So for the powering of the Amazon, diesel power generation has been subsidized, but not photovoltaics. This changed now, but this has to be considered. Risks management is also a thing that should be considered. What's the failure rate of the equipment? Is there a risk of theft? This is also be included. Also financial risks for the financing. If you have some considerable risk, it may increase the interest rate. The cost of the capacity storage. Eventually, you have to pay penalties if you don't deliver the power, what has been planned for or what is written in the power purchase agreement, PPA. The lifetime expectation. Different components have usually different lifetime expectations. For example, PV panel lasts between 25 and 30 years. The power electronics, you consider about 10 years. Battery, depending on the type of battery and the temperature. If you have a lead-acid battery in the tropics, lifetime may be 2 to 4 years only. If you are operating at cooler temperature, it may go up to 10 years. Also, the depth of discharge plays a role in the lifetime expectation, and so on. In the number of cycles for sure. Emission trading becomes more and more important since this year emission trading is given by law in Germany by a fixed rate of 25 euros per ton. This has been different some years ago. This was quite subject to some speculation, and also the value of the emission of the carbon dioxide changes a lot. But Germany, there's a quite fixed path now for the increase of cost of carbon dioxide in the next 5 years, and this has to be considered here also. In future, the value of the emission trading can be more than the actual electricity sales price. It depends also on the surrounding, depends also on the grid. For example, if you live in Poland, there's a lot of coal power plant, and if you substitute coal power emissions, this is much easier. For example, if you would install a PV system in Norway, which has 99% of hydropower, which is already clean, and so you're not able really to get some emissions benefit out of photovoltaics. So typical results as an output are so the rated capacity of a PV systems or other components, the wind turbine, for example, total annual electrical power production or energy production, the penetration of renewables in the systems and the related carbon dioxide emissions, the necessary converter and inverter power output. So it's not only the energy which is relevant, it's also the maximum power being delivered, because this defines the cost and the size of the converters and inverters. The battery system, so there are many parameters. You have the storage capacity, you have the voltage that defines the number of cells in series or in parallel, bus voltage, the hours and days of autonomy. Remember when we designed the system manually, we just took it very easy. We said, okay, 2 days for a system in the tropics of autonomy and 4 days for Germany, but you can do it much more in detail. The system costs, the annualized costs, the actual costs of energy, and the so-called net present costs, which I will present later when we go into Homer. So cost of energy, this is the average cost per kilowatt hour of useful produced energy. And component costs, the replacement costs, capital costs, maintenance is also quite important. It's not only the material, you have to send someone there to replace the equipment, and this cost has to be also considered. And as I mentioned before, the net present cost, this is the present value of costs of all system components minus the present value of revenues over the project's lifetime. We see here a tutorial from PV-Soll. This is a German program developed at the Technical University in Berlin by a colleague of mine, Dr. Valentin, and he started doing a simulation program on thermal simulation. Next step was it to the PV simulation. This is quite nicely made. It even contains a 3D simulation, so you see the shadows during the years. So this is the input, so you see this welcome page. You can either start a new project or reopen already begun. Also sample projects. But here we will take a look at the new project. First you enter the project data. So you can always switch between the different steps, between the buttons. You can also put additional data there, which will be contained in the final presentation, for example, for the client. Also a company logo or your university logo or whatever. So this is the technical layout of the system. You see there are some modules interconnected in series, and the inverter, a kilowatt hour metering, and the grid connection. So you can select this here. also whether it's autonomous systems or grid connected system. Then you can select here the location, for example, Germany, Berlin. So it automatically contains the Meteonorm database. So here's 3D. Funny-wise, if you include, for example, trees, it contains not only the shadowing of the trees, it contains also the seasons. So if some trees lose their leaves in winter, so you will have more light in winter, some's not. Even includes an option of the growing of the trees. So for example, this system is going for 25 years. The years the trees are growing and causing more shadow. Here you can select the location, the different views from the top, from side view, define the area where you want to implant your system, also the orientation, north, south, and so on. Here different roof types, different plant types, or tree types. Yes, you can hover around and see from different angles and so on. As you know, it's probably from Google Earth and so on. So here you have the orientation, elevation, and so inclination. Some terrain is not flat but inclined. You can also enter this here. Different azimuth orientations. Terrain views I mentioned already with the different trees here. You see already the shadow here, the sun. So it depends, as mentioned, the size. I think the new version is just an older version in this video, which was supplied by Valentin. The new version, it even considers the growth of the trees. While the trees, different types of trees grow in a different speed, this is also considered. So you have to exactly give the type of tree which is there to calculate the growth correctly. Here you have usually a large database of different modules, but here's a custom-made use. And this database always updated because the manufacturer, they give new, more efficient solar modules. Latest trend is bifacial, it's included in the software, and the others, Homer is not included yet, the bifacial modules library. So the different configuration, how you set up the modules, and you can also have the options to fill the area with modules and so on, or you give you have a defined number of modules and you can arrange it differently. For example, here just making one row, or you can make 2 rows with 10 modules each and so on, and this is done automatically by resizing the available area. Here you can make 6 rows, 7 rows, or something like that, or make larger one and see how many modules fit in there. It also does a calculation of the shadows and the losses per year is usually indicated by color. So red color means severe shadowing, severe losses, and green is no shadowing and so on. We see it later. So we see here some models are subject to shadow now. Now we can do a calculation during a whole year and see the different losses. I know it's not done it here. You see the different configuration first here. Different distances between the rows. So also to be decided for the modules, but also the inverters are quite relevant. Can use one central inverter, but it is most preferable, especially if you have shadows, to use multiple inverters. You saw the most extreme would be the module inverter, so each module would have a separate inverter. But in this case, they use string inverters for every row. You have one inverter, and each string will operate separately. So you can choose to take a look at the different range of maximum power point tracking capabilities. Here we saw what I mentioned before, the loss is due to the shadowing, so the red part is subject to shadowing, the green part is okay, the yellow part is almost okay, and so on. So you can have different threshold and so on. And best is just to interconnect the modules which suffer from the same shadowing to one inverter, so the good ones wouldn't be interfered by the reduced current from the shadowed rows of modules. The configuration, there are two strings attached to one inverter. Depending on the type of inverter, whether it's just a pure string inverter, which really has one string, but you have also several ones. Also the number of modules, as we calculated already, depending on the maximum system voltage. And the maximum power output of the inverter. From the input side, it's important that you fit to the range where the maximum power point tracker can act under all conditions, so for cold conditions and hot conditions and different irradiance conditions also. So it simulates now the energy yield, also the financial yield, and at the end you will get a report. So here you see the different yields during the different months of the year, which is usual in Germany. You have during the summer months, you have the highest yield. In winter, it's rather low. Performance ratio, consider the performance ratio of the inverter, of this whole system, of the modules, and so on. Then you can save your simulation program and so on. Download a free version here under this software, the trial version, and I think it's quite limited to some locations, but it's quite interesting to see what the software is already capable for. Here's also a more sophisticated presentation here for design of a roof of a commercial building in Miami, how they carried it out without being there, just using Google Earth. Let's see how this works. Basically, you transfer the bitmap from Google Earth into the PV Soul software. First, you have to have do some measurements to do the correct sizing. So you have to have the height and the length of the building and the width of the building, and this shows the whole process for that. So you just choose the location where your building is. So it's in Miami. Here is the building on the lower left side. So you amplify and you go to the 3D mode of Google Earth. We have to carry out some measurements. For example, we start with the height. Take a ruler here, take the ruler option and measure the height. So write this down, 23, almost 24 meters. This is a top view. Also, you measure this side here, 1 meters. Also, you have to consider obstacles on the roof. Measure also that height. Which you need later if you're going to the Valentin or the PV-Sol software. It's from top now. Okay, you have to put the right orientation, so it should face north. It's done here now. So I have all the different sizes, measures in the correct orientation. Now we take a screenshot of that and go into PV-Sol. There you can import this screenshot and calibrate it correctly by using the measured sizes as well from the width and the height and length. For the Irradiance data, you have also put in again the location there. Now you load the bitmap there. Would be much easier, it would be a vector graphic, but it's only a bitmap, so you have to make your polygon, vector polygons on your own. This is shown here now. Teach the program what's the appropriate area, size, and so there's shape and so on. Drawing this vector polygon, which indicates the available area for the PV system. You have to consider also the not available area, which is defined by what this is in the middle, kind of air conditioned equipment, which is 3 meters above the possible area. Just given the height, it's relevant for the shadowing here. We make a 3D object with the measured height from Google Earth. So you can automatically assign the modules, but you have to give the blocked or forbidden areas first. This we do now. So it's 3D extruded at the correct height. So here they choose the orientation, this 180 degrees of azimuth, that means orientated towards south, the correct elevation angle of the modules. So it automatically calculates now the optimum coverage by the modules. So you will have some shadowing for modules which are close to the obstacle, at least for some parts of the year. And this is calculated here now and will be indicated by different colors. So green is okay, but yellow there is some shadowing. It's also a forum if you want to discuss it. It's available on the internet here. There's another program called PV-Syst. Usually the PV-Sol program is used for roof-mounted systems and mid-size systems, while the PV-Syst is really designed for really large systems which are not mounted on roofs but more on open field. The PV system side or PV side is a bit more sophisticated, because also derived from a Swiss institute which was formerly working on PV semiconductor technology. Hence you can have a free version for 1 month, fully working. It shows you how to install it.
Welcome to another PV-Syst tutorial. Today we are going to look at the installation, configuration and first run of PV-Syst. To download an evaluation of PV-Syst, you may go to pvsyst.com in your web browser. I am using Google Chrome. Open pvsyst.com in the browser. You can have a look at the website and read some basic info on the software. To download PV-Syst, click the Download PV-Syst link. This will take you to the download page. In the download page, you will find all details regarding the software and the system requirements. Here you can see the different versions available for you to use. When we download PV-Syst for the first time, we will get a 30-day evaluation version. It has all the features, but the result generated after the simulation will have watermark on it. indicating the report is generated using the trial version. After 30 days the software will change into trial version, where the functionality is limited. It is still good for learning, but not for real-world problem solving. This piece of software required to have a Windows machine with version Windows Vista or above. It required .NET Framework 4.5 installed. I do not recommend using a Windows XP. PV-Syst will not function properly in Windows XP. Please make sure your computer have all necessary hardware and software installed. Click on the Download PV-Syst link to start download. As you can see, the software starts downloading. The download has been finished and we can launch the installer. The installation is straightforward. Click Next on the welcome screen. Read through the license text if you prefer. Agree to the license by ticking the checkbox. Click Next to continue. Here you can change the installation directory if you like. Click Change and choose a location if you want. Click Next to continue. Click Install to start the installation. This will take around a minute to complete. The installation is now complete. Click Finish to exit the setup. To launch PV-Syst, double-click the desktop shortcut. You can check the license status here from the license menu. If you choose to buy and activate your product, you can use this window. Here you can choose your language. The interface has 4 main options to choose from: primary design, project design, databases, and tools. I will talk more about the interface and these options on the coming tutorials. Thank you for watching. Stay tuned for more videos.
So now we come to a demonstration of the software Homer, which is simulating entire microgrids. So not only the generating components as we saw before at PV-Syst and PV-Sol, but also including batteries and backup generators and so on.
Hi, I'm Lisa McDonald, and today I'm going to show you a quick tutorial on how to use the Homer software program that can be accessed through the Department of Energy's website. And this Homer software is a great tool to use to analyze different renewable energy systems that are the most optimal and energy efficient for your business or home. So to get started, look up here at the top left corner of your screen. You can see equipment to consider. I've already started a project on wind turbines, but if you hit this add or remove button, you can add or remove any type of system you're interested in looking at, whether it's solar panels, hydropower, etc. You can add multiple generators and multiple batteries to your desire. You're also going to want to consider whether or not you're going to connect your system to the grid or have it as a standalone. If you want to change any of the specs on your generator, your converter, or your battery, you just click each of their little icon buttons, and all of these screens look the same. So I'm looking at a quantity of one generator, an example of a capital cost of $1,500, replacement cost of $1,200, and your operating and maintenance cost. This one's 5 cents an hour, but it can be per hour, per day, etc. Hit OK. Next, you're going to look at your resources. Since I'm only looking at a wind turbine, I only have wind resource data here. I've already uploaded a time series data file into the Homer software program. You can manually input all of this data here, however it's pretty time consuming, so I'd highly recommend having a data file ready to go so the software can analyze that pretty quickly. Your fuel source, this one's going to be on diesel, however you can change that, especially if you're looking at a solar PV system, if you want to run on natural gas or biofuel, etc. Economics, if you click that button, you can analyze different interest rates and lifetimes of loans. Hit OK. If there was anything that wasn't syncing properly with the equipment I've considered up above and the time series data that I've already input, Homer would give me an error in this section here where it says document author notes. If I clicked the little eyeglass button, it would give me a little more description on what that error is and how I can fix that. So right now I'm going to hit calculate. So it's going to calculate the most energy efficient and optimal renewable energy system that I'm looking at here. These are the two most optimal for my project, and these buttons here indicate what's included in your system. Of course, the most optimal system here does not include a wind turbine. However, that's because the initial capital cost is so much lower. I'm prepared to spend that initial capital though, because I'm really interested in putting in a wind turbine. So if I look at this system here, it shows me my operating costs are actually a little bit lower at $21,000 per year, which is offset by that renewable energy that I'm producing. My total net present cost of the system is going to be about $337,630. My cost of energy is going to be roughly 85 cents a kilowatt hour. If I double click this here, it actually goes into quite a bit more detail on all the different specs on this project that I'm running. So you can see I have one 10 kilowatt wind turbine. I've got a 15 kilowatt generator, size 8 Trojan L16P battery, and a 6 kilowatt inverter. Here's a breakdown of some of the costs, net present costs, cost of energy, and my operating costs. You can look at the different cash flows here, gives some great examples of bar graphs, etc. Another thing I'm really interested in is the electrical output. So this is showing that the wind turbine is going to produce about 8,337 kilowatt hours a year. And it's going to also have an excess electricity amount of 18.4%. And then you can just, go through all these different tabs, have some great graphs that you can use in your presentations. And I think this is a really great software program to use to analyze different systems and find the one that's most efficient for you. So I hope you enjoyed. Thanks.